I would like to talk about IQ, but I do not have any research on IQ. I'm actually here because me and Professor Durlov have been kind of studying twin effects very recently. And the idea was actually kind of try to get kind of twin effects and get another look to see if we can use twin effects to have kind of some tools of identification that are a little bit kind of beyond what the literature has. And we have kind of been studying this thing kind of very recently. And at the beginning, I thought that was a quite interesting topic. But then I saw a presentation of Professor Rousseau, and that's as interesting as it gets. Well, this is the standard confounding model of economics. Let me try to explain what it means. It's a DAG, direct acyclic graph. We have x, y, and v are random variables. When I put these arrows over there, I'm just saying that there is kind of one autonomous equation that links each one of these variables. And this autonomous, I mean that you can change the arguments of the verbs. You're not going to change the equation itself. And there are kind of error terms that in this graph I'm not kind of showing over there. Why this model is important? This model is extremely simple. And this model is important because most of the identification models in microeconometrics, you can boil down just to identify this model here. If you can identify this model here, you can identify all the models of generalized Rye model, and you can do way beyond average treatment effect. You can do marginal treatment effect, policy relevant treatment effect, and so on. And what's the main solution in economics to this model? It's the IV solution. You just kind of stuck one instrumental variable over there. And if you put one instrumental variable over there, you can really identify this model in a bunch of ways. Now, in the most general way to actually kind of present this model is not identified. I mean that without kind of any other assumption, I cannot actually identify this model. I need to put some assumption on the relationship between kind of this arrow over there on z to x. I can also assume simple linearity. Then I have the standard two-stage less squared, then can identify the relationship between x and y. But there's a huge amount of literature that actually kind of identify this model using kind of far less assumptions. So the idea is that we are going to kind of get kind of an instrument. The instrument is going to be independent of v, which is our confounding variable. That is actually going to get kind of a spurious relationship between x and y. And x is going to be independent of z, condition on x and v. These two independence relations completely characterize the DAG, direct acyclic graph, that I put over there. I can also kind of write the instrumental variable in terms of counterfactual outcomes. The counterfactual outcome of y, when x is fixed at little x, independent of z, condition x. And I have that actually kind of z is independent of v. And there are a bunch of kind of ways to identify this thing, as I said. For an unbiased citation, Pinto 2013 says that you have kind of each one of these statements are actually equivalent. And if either one of them holds, you can actually identify treatment effects in a categorical model. But the idea was actually kind of, in a very basic level, try to understand what kind of twin data, and actually kind of try to extract some properties of the twin data that I can kind of create some identification criteria. And twin data, in the most basic level, you pretty much have kind of only two properties. First thing, twins share to some degree the confounding variable causing outcomes. This is the V that I put over there. And then you have this independent variation that while monozygotic twins share the same genetic endowment, dizygotic twins don't. So pretty much kind of we have kind of very limited properties here. Might that have x1, the variable x, trait x for the first twin, x2, the trait for the second twin, and you have some unobserved confounding variable v, and we know that kind of this v is correlated, is related to each other, do not know why, do not know how, can be kind of a very complex process over there, and you also have that kind of some set of the variables of vx1 and vx2 are actually be the same if they are monozygotic. And that's kind of the first thing that...
Why do you superscript the v's with x? What does that mean?
Oh, I'm doing that because this little framework here, I'm using kind of a bunch of models, see? Just because of that.
Rodrigo, I'm not sure that answered. I'm sorry to be teasing you. Just these aren't notation that everybody's going to be comfortable with.
Yes. They're simply because I'm going to have kind of a bunch of these v other subscript. But v, one is associated with x1 and another one is associated with x2. Simple like that. And then, well, based on the characteristics of the twins, we can actually classify the confounding variables in these 4 groups. The one that is equal only if twins are monozygotic. The one that are equal if, regardless of the type of twin, monozygotic and dizygotic. All the rest of the variables I'm going to call confounding variables, and I'm going to use an exclusive restriction. There's no confounding variable that's equal for dizygotic and different from monozygotic twins. And there's kind of this little table here. And this indeed gives some properties of the variables that we are going to do. This you can actually kind of define the variables according to a model. And you have kind of the first one, you have the genetic endowment of the first twin is equal to the other one, when MZ is going to be kind of indicator function that takes value 1 if twins are monozygotic, and those variables are equal. The second one is the shared environment, and the C's are equal for both twins, regardless if they are monozygotic or dizygotic. Then you have kind of non-shared environment. The non-shared environment, it's actually kind of an assumption to see kind of that they are independent. Indeed, what we have is that they do not comply with kind of the first and the second approach. But there are kind of some theorems that says that you can kind of express x1 and x2 into kind of a term that is common to those variables and other 2 terms that are independent. If this is so, you get the first term and put this into the shared environment. Then you have the x1 is independent of ex2, regardless of the monogodicity of the twins. And for sure, this model does not justify the independence between A, C, and E, as usually kind of claim in the models. But what people do with kind of this sort of model? That's kind of the standard univariate ACE model. I'm going to start with this to actually kind of explain what we can do out of this. And as you all know, we have kind of x1, trait of twin 1, x2, trait of twin 2. Now I have kind of these little letters in each one of the arrows, which says that kind of I'm using kind of a linear model. And with this model here, we can get kind of the variance decomposition. And we can also get that epsilon 1 and epsilon 2 are independent of all variables. And we have kind of these properties of the shared environment and the environment endowment. Standard critical of this model that there's no gene-environment interaction. And then we can also kind of apply the same approach to the bivariate case. The bivariate case, we have kind of the x over there, the confounding variable. And we split the confounding variable into kind of these 3 sets of variables. And then I have kind of all these arrows over there. And these arrows provide kind of a model that is identifier. That's the bivariate ACE model. Observe that I do not have relationship between x and y, because I believe that kind of the basic approach of the model is still kind of decomposing the variance of this of x and y into share, unshare, and genetic endowment of the twins. But the goal of economics is not kind of actually kind of share this variance. It's really kind of try to estimate the causal relationship between x and y. And again, how can we use kind of twin data to do that? One approach is just kind of get the previous bivariate ACE diagram and actually kind of put kind of a causal link that we would like to estimate, x and y. And then we get this causal link over there. Unfortunately, this model, even kind of the linear case, is not identified. And it's not identified because we actually kind of have the relationship between the epsilon x1 and epsilon x2 into y1 and y2. So what is kind of the standard economic solution to this problem? What they do is simply get rid of this causal link.
I'm sorry. I don't see that in the stack. So the x1 and the y's, there's colliders on all paths between them. Why are they associated?
I'm sorry, can you repeat? There are colliders?
So did you say that the xy1 and the x2y2 are associated?
Yes.
By what path? There are colliders on all of these.
Yes, these are twin x1 and x2. This is kind of the genetic endowment correlated. This is kind of the shared environment. And this is kind of the genetic environment of second twin, shared environment of second twin. And then you have the uniqueness environment of both of the twins.
Sorry, I just didn't see the arrowheads. I'm too blind.
Okay. And then again, this model is not identified. And most kind of economic models just identify this model by a simple trick. Get rid of this arrow. But when you get rid of this arrow, you are pretty much kind of identifying this model here through an assumption. Because you are saying that all the variables that actually kind of provide some confounding effect in the model A1x, C1x, YX, and CY1 are actually kind of related to the x, just to the x and y, just in this part here. So when you get kind of a differentiation between x and y, you get rid of kind of all confounding variables, sort of by magic, isn't it? And so it kind of has a very strong assumption to identify this model. And most important, it actually gets rid of kind of the half of what is interesting about twin models. Because we do not use kind of the second property of the twin models, the part about monozygotic and dizygotic twins. Indeed, we can identify the model only using monozygotic twins. And what the model tries to do is actually get kind of this old idea of IV of economics. Indeed, the difference in x is independent of the variables creating the confounding effect, and the different x is not independent of x. So it's pretty much kind of create kind of a great IV.
Sorry, Rodrigo, can I just take you back to the last slide? I just want to make sure I understand. So what are we assuming away in the standard economic model?
You're assuming the effect of the error term x1 into the outcome y1.
Okay, so that's the standard.
Yes, that's the
orthogonality condition.
Yes, I just went fast because I believe that I'm the one that kind of I believe that you all know this model. Yes, some people say yes, we know this model a lot. That's kind of bivariate kind of ACE diagram is identified the way it is, and putting the bit over there, that would be kind of traditional approach, becomes kind of unidentified, but get rid of this causal effect here, makes the model identified again, ACE beta, and that's kind of the standard model of economics, and usually identified by standard twin fixed effects. And again, you do not have kind of gene-environment interaction. But the interesting point of actually using kind of ideas of this model is not identify this one, because, as I said, does not using kind of the property of zygotic twins, and it's pretty much kind of identified by assumption.
Sorry, so you don't need the monozygotic and dizygotic difference to estimate beta?
Yes.
Okay, but to estimate the other things, you need them, right? To estimate the effect of A and C on X and Y, you need those, right?
Oh, yes. Yes.
Okay.
But not beta, which is kind of the standard part that we'd like to estimate. And the interesting part, the model that kind of I would like kind of to actually estimate is a model like this. And this model is completely non-parametric. Instead of having C1 and C2, you just have kind of a single C that kind of affects all of them. Instead of have epsilon 1 and epsilon 2, you have kind of epsilon 1x and epsilon 2x. You have a single x, because all these parameters are not important to actually kind of estimate the causal effect of x1 and x2. And then you have kind of a variable here that's kind of the monozygotic variable that affects kind of both the genetic part of twin 2 and twin A, and also the genetic part associated with variables y1 and y2. And again, this model is completely non-parametric. The previous model that I told, the IV model, you have kind of only two independence relations that characterize the whole model. This model is a little bit more complex. Indeed, if you apply simple tools of Bayesian network, and then apply some tools that call graphic axioms, you generate 431 condition independence relations. Out of those, most of them they're not as general as can be. If you get kind of only the most general ones, you generate 141 unique condition dependence relations. This model cannot be represented simply as a DAG. And by this I mean, I cannot represent this model simply as kind of the causal relationship of variables. The twin data set gives kind of more information to us than the simple causal relationship. It indeed gives kind of 4 additional independence relations, and also kind of some equality distributions. And this is kind of the problem setting that we can use using kind of the same basic assumptions of the fixed effect twins, but in a completely non-parametric way. And I have to confess that the last 4 days I really burned the midnight oil. Professor Durloff is here, he's witness. And I almost identified this model, but I couldn't get it through yet. The planets were not aligned yet. Well, hopefully soon. And this is kind of the non-parametric model of monozygotic, using kind of still kind of the independence relation between A, C, and E. You have kind of a simpler model, because then I can get rid of the monozygotic variable. And then you have kind of a less condition dependence relation, and you still have kind of the same distribution addition dependence relation and distribution equality that we had before. Even though I didn't see the identification of that model, we actually kind of took our classical example of ACE model. And in this case, I'm just going to use kind of simple example that did some days ago. And we are actually kind of try to examine the intergenerational elasticity equation, which is usually represented by a parental income. Professor Justini did come something close. Instead of using kind of a AR1, we use kind of ARMA 1, isn't it? Then a parental income is beta times kind of y, which is descendant incomes plus an error term. And beta is not actually kind of the parental income, has a kind of direct impact on the descendant's income. The beta itself is kind of a parameter that kind of summarizes a huge amount of relationships that actually kind of confounding effects of both kind of x1 and y1. And the interesting part that we are going to do here is that instead of kind of estimating this model here, we are going to use kind of the twin data set to see if we can actually kind of explore a little bit this relationship. So in this case, we actually have the second part of the twins. And I'm assuming that parents are twins. So I do have kind of confounding effect on y, but they are not kind of related. And I have this confounding effect of V1 and V2 here, where the second property of the twin data, the monozygote and dizygote, operates. Well, if they are twins, I can always split the data into the three terms that we discussed before. Now, the interesting part here, where it's different from the previous beta ACE model and also the bivariate model, is not that is that we do not want kind of these relationships between the confounding variables to be independent. Instead, we want this thing here. We want kind of that each one of the confounding variables of the parent twins actually affect the confounding variables of the respective children, and then you have the effect of x in y through this dynamic of unobserved confounding vectors. And this model here would be kind of very nice to estimate this model. However, this model is not identified. It has kind of a other problem as well. In this model here, the variance of the income of the parent is equal to the variance of when you have kind of dizygotic and monozygotic twins, they are equal. And this does not comply with the data. But we have kind of a way to solve this problem. Just make it a little bit, just generalize and make it a little bit more flexible by allowing the cross-fertilization of twins genetic endowment. What I'm saying is that while this model here is not identified, this model here is. When I actually allow for the genetic content of the sibling of the twins to affect the income of the other sibling.
Between the identified and not, can you toggle between the identified and the non-identified and miss which arrows appear?
Oh yes.
So you add arrows and you get identification.
Just that. Yes, there are.
Relax restrictions.
Oh no, I see. That's kind of a very interesting point here. Because I'm putting kind of one more arrow. So I'm getting indeed kind of one more parameter, isn't it?
Oh, so you're restricting the parameters of these two arrows to be identical? That's the idea?
No. Yes, the parameters are always identical. For example, this is CXX, this is CXX, they are twins, and indeed the distribution of X1 is equal to the distribution of X2. But the point of this parameter here is that instead, it's a completely linear model, so I'm indeed kind of put one more parameter. However, I'm creating kind of almost doubling, actually I'm creating kind of almost doubling half of the variance matrix, because now I have this parameter here, but the relationship between A1 and A2, it varies for monozygotic and dizygotic twins. And this kind of create kind of more relationships because this relation here, because of the dynamics of the confounding effect, it is spread to the whole kind of covariance metric that I can get out of the data. And then we can also kind of estimate the bivariate model that actually have these parameters here and allows for the both kind of well, now it's a bivariate model, not kind of a twin parents and children, but kind of both of them are twins. Everything is linear, yes. Yeah, the other one, the difference between kind of previous one and this one here, because now, before we have kind of parents that were twins and children were not. So these kind of are actually kind of different people. And in the bivariate case, they're actually kind of the same people, but two measurements. And you have kind of monozygotic and dizygotic, monozygotic and dizygotic twins operating both X and Y's. And that's it.
Those are twin children of twin parents?
These are twin children. These are the children. These are twin parents, and these are the children of the parents. And what I'm doing kind of the confounding.
When you asked the last one, do you also need twin children of twin parents?
No, this one is just kind of imagine that we have kind of the previous bivariate model. It's not kind of a age model anymore. It's just kind of a bivariate model that I have kind of two measurements of kind of one twin and two measures of the second twin. It's just that kind of when I identify this one here, I also kind of identify this model here, but it's a different model for a different purpose.
Do you mind if I add some marketing?
Yes.
You were done or not?
Yes, I'm done.
Okay, first, thank you. I meant by marketing is to pull out 2 points. One of them is that there is this machinery that has been developed both across statistics and social science talking about causality, which is trying to roughly, sloppily speaking perhaps, allow one to make counterfactual statements, such as if the genetic input were different, what would be the difference in the outcome? And the philosophy behind it was to avoid parametric assumptions and the like, asking about the question of directions of mechanisms and the like. And so the first objective in this work is to translate the twins literature into the causal framework and ask what is preserved in terms of identification versus what is lost. And the second, Genet is an inspirer of, and that is to sort of unify the different aspects of the kinship models using the causal framework so that we can talk about what the information is in the children of twins versus the twins, and it's all kind of put together and you can see whether or not collectively how things are shifting. Okay. Doing justice to the agenda? Yes. Very good.
So one thing that occurred to me as I was watching what you want to do, what you're trying to do here, is there are some models out there in the twin literature that sort of, that model I want to talk to you about, but that's not my point right now. There's a model that Andrew Heath published more recently. I think it's Andrew. Can I have somebody? The causal model. Yeah, and then more recently by Nathan Gillespie that does attempt to get at causation within a twin model without having longitudinal data. So you might want to take a look at that. It requires, I don't know if your model requires this, but that model requires an imbalance in genetic and shared in the two constructs that you're interested in, and that's the way you can estimate the causal direction.
Oh, that's nice.
Yeah. The one you did just put up with the same A going to the two different variables, or the same C and the same E. I think that's not where you landed, but that presumes that there's that the shared environmental influences and the non-shared environmental influences are the same for the two constructs, which doesn't seem tenable.
No, that's quite interesting, because if you're using kind of a linear model, you tend to understand this variable here as kind of as a value, not a vector. So it's really kind of a single random variable here. It's a scalar. But when you're in a completely non-parametric model, this C here can be actually a vector. I'm just saying that in a completely non-parametric model, that makes no sense for me to put actually kind of multiple C's here, and all of them kind of one C kind of enter here, entering here, another C entering there. Given that I'm not going to estimate the C, and I'm really kind of focused on estimate the causal effect of X1 and Y1. And this C here can be as general as I want. So indeed, all this kind of a shared environment that only impact Y and X and kind of and you can think about, you can think this C here as kind of an infinite sequence of C's, all of them connect to each one else, and also kind of connect to X1, X2, in both for both twins. So this C captures kind of all type of generality that you can think about C1 and C2,
I see.
like CX and CY and so on.
But you're not interested in estimating the effect of C on the X's
Yes.
and Y's, right?
I'm only interested in computing the effect of X2 and Y2 and X1 and Y1, that's it. And for this model is as general as the other ACE models.
Which is why this is what I have, right? Without further assumptions.
Oh no, almost there. Do not say that yet.
So
Will be,
said
will be.
This DAG was, now you said this was not parametric, right? And C is latent, it can be anything, so it's not identical.
Oh yes, the C is not identified. The only thing that I'm identifying here is really kind of the causal effect of X2 and Y2, and that's it. For instance,
You're saying non-parametric, without putting any structure on the stack, you can identify X1 and X on Y1?
work on that, likely, because you have kind of really kind of a lot of things that you can use over there. And
I'm
you have,
sorry, Rodrigo, I can't hear. I mean, but I'm just trying to figure out what you've said before. So before you said you need to put in some structure to get identification. Now I hear you saying that this general DAG is non-parametrically identified.
these for sure you need to put more structure, because this one here you're not
That's
you're
not identified.
not identified. But observe that this DAG, it's completely kind of explained as a DAG, and you do not have any further restrictions. I mean, this is a simple DAG that has kind of a confound effect associated with X and Y. In the case of the twins, I'm actually going to put lots of restrictions over there.
Okay.
So for example, so I'm actually kind of making kind of all these confounding variables E, C, and A complete independent, see? And then this kind of gives a, moreover, not only they're independent, but I also have kind of the independence relation and kind of distribution that kind of the twin data set gives me sort of for free. Just because it complies with kind of how the data is generated. These further restrictions comply with the data is generated. So it might be kind of, it's likely that kind of with this restriction you can identify this causal effect.
I love this agenda, and I'm just, you might have said this and I missed it, but I'm wondering, what is the intuition behind how you're going to use the twin natural experiment to identify the effect of X on Y?
Oh, so let's get kind of the intuition of this model here. And the intuition of this model here is that, imagine that you have kind of a confounding variables A, E1x, A1x, C1x, AY1, CY1, AY1. Imagine that they have a stable distribution. So the variance among them kind of is equal. But then you allow kind of all of them to correlate for the parents to the twins. Okay, this correlation between kind of the variables actually kind of it's actually affected by how correlated are these A1 and A2. So if I actually kind of put one more relationship between A and X, this create kind of more constraints when I analyze the whole covariance matrix of the model. And when I get kind of dizygotic and monozygotic twins, I just kind of generate more equations that I use a constraint to get the parameters.
I'm just, the intuition you're giving is kind of a mathematical intuition, almost like a proof sketch. And I guess I'm groping for a very, simple verbal intuition, if there is one.
It's still a difference in intuition, right? It's still a difference in intuition. I mean, like you're still differencing. Like you put structure on the effects of your latent variables on the observed variables, and then you put some restrictions on how they'll essentially cancel out. Right.
No, they're not cancel out. They're actually kind of they generate more equations, because when I put kind of a more when I associate genetic factors, when I put more links in genetic factors to observed variables, then I can actually have kind of more restrictions when I do the conversion of the observed variables, because I'm going to have kind of one set of restrictions that before operated for both monozygotic and zygotic, and now I have kind of one that operates different for monozygotic and dizygotic. And in this case here, the intuition of this model here is simple, isn't it? You get rid of all the confounding effect when you take the difference. And the idea here is actually kind of using the part of monozygotic and the way it changed the relationship between A1 and A2 to actually try to manipulate the relationship among the distribution of these variables and try to get the cause effect of this one and this one. And how you do that? You really kind of try to express. I can go in detail how you do that. First thing, this is kind of the empirical model. You create a hypothetical model, and this hypothetical model got rid of this arrow and this arrow, and I put kind of a hypothetical variable here. This hypothetical variable is going to impact y1 and y2. This second model is going to generate a bunch of restrictions, conditional independence restriction and distribution restrictions. Then I express the expectation of x1 and x2, the expected y1 and y2 condition on this hypothetical model. And this is going to be expressed in a bunch of distribution for all these variables. And then I see how I have kind of 4 little terms that associate the empirical model with the hypothetical model. And I try to express the hypothetical distributions into observed distributions in the empirical model. And that's where you identify.
So I'm moving much slower than you, but let me tell me if this is basically right. The idea is that you have differences in the x's within a pair, and you're basically using the mz versus dz as a kind of exogenous shock to the degree of similarity in the x's across the twins in the pair, and that's the, still don't fully see it, but that's the source of exogenous variation.
Yes. Source of variation. And maybe, for example, but it's quite hard to see as well how you can identify this model here, isn't it? Because this model here, you can think a lot about kind of how you're going to identify this model here. Oh, I have kind of some dependent variation z is causing dependent variation in x, and then how it's going to cause some independent variation in y, but then you have kind of counterfactor. Just to see this model and understand what will be the restrictions that you put in this arrow here to actually identify the model is a quite complex feature, isn't it?
You could still get balanced without any restrictions.
Oh, on this, yes. Both of them, indeed. In each one of the mods, indeed. In this model here. In this model here, I can only get bounds in CX, AC, and CX.
And I think that's one of the virtues of the approach. It's something you said in your talk, Paul, about whether a given study is giving you some sense of magnitudes. This is precise the notion that these contributions are not identified by some auxiliary assumptions, but nevertheless they can be bounded, and that could be quite informative.
See, the MZ over there, it's close related to an IV. See, if you didn't have kind of these 2 arrows here, the MZ would be kind of a simple instrumental variable. But if you didn't have this 2, you could get rid of AX and AX2. You just put kind of MZ associated with this, and all these covariates you can just kind of put a single V here. And this will be kind of simply an error term of x1 and y1 and y2. So in that sense, MZ would be kind of an instrumental variable. But it's not. It's not because of this relationship directly to this endowment that affects you. So it might be the case that you will like identify this model here by putting some type-like of IV restriction in these 4 causal links. But this one I do not know yet.
Can I say just one thing to the people? The guy who invented instrumental variables was Philip Wright, a Towson alum who was the father of Sewell Wright, the geneticist. So maybe now, and in fact, some people think that Sewell Wright, the geneticist, was really the guy who invented instrumental variable. Although Jim Stock at Harvard has proved that that was not the case. It was Philip Stock. But what I think Stuart Wright did was making the math so complicated that when Philip Wright submitted to the QGE, it got rejected because they didn't understand what he was doing. So eventually it had to be published as an appendix in a book about Paris when Philip Wright wrote the book. So by bringing now some of the econometrics and the approach, in a different way to genetics, maybe it's the revenge of Philip Wright or the return of the rights.